All right, well, welcome to another fun-filled day of calculus. Today we're going to pretty much pick up where we left off. We're going to keep talking about limits. We're going to practice some more, doing some more algebraic techniques so that we can use the laws to evaluate the limits. And then I'm going to show you some that involve trig and things like that. And then we're going to turn our attention to another big idea that we need to do or have to do calculus, which is the concept of continuity. Okay, so that's our plan for today. Before we get going into that, though, I'm just going to ask if there are any questions on the homework. I imagine that since homework's not due until next Monday, we may not have a lot that have popped up. But any questions at this point? No. Okay. Well, that is totally cool. All right. Well, then I'm going to go ahead and switch screens, and I will see you up at the whiteboard. All right. So last time, let's just kind of recall where we are, what we've been doing, so that we know where we're going. So we've been talking about limits. And remember, the whole idea about limits is that we're interested in what's going on near a point. So we don't really care. We're not too concerned with that specific x value, but we want to know what's going on as we get near it, right? And so that's just a little bit different of an idea. But the way we write it, of course, is limit as x approaches c of f of x. I'll go ahead and say equals L, just so that we've got a number. Obviously, it's a letter, but letters are numbered. So again, we're just looking at what happens as we get close to C. So we've looked at it numerically. We plug in values, kind of see if there's a pattern. We've looked at it graphically. We draw the picture. We think about the little spider or whatever walking on it, figuring out its elevation. And we just started working on it algebraically. So in terms of evaluating these, step number one is try plugging it in. Because we've seen that when we plug in C, when we actually plug in C, we often get the limit, right? So we're going to plug in C, and really, the only thing we have to worry about is we're going to have to do some algebra, trig, etc. if this isn't defined. So if we end up with like division by 0 and things like that. So that's going to be really our first step. It's just plug in C. And if it works, great. If it doesn't, well, then we have to pull some other trick. Okay. And so in terms of the big things that we try here, we mentioned a couple of these last time. Big things are going to be factoring. Do that a lot when you have polynomials or rational expressions. Rationalizing. And we do that when we have roots. Excuse me. And then another big one we'll use from time to time are identities. But we're going to add to this list, and in fact, we're going to, like I mentioned last time, be doing this for, well, the rest of this year. Things will pop up that will help us when it comes time to evaluate limits. Excuse me. All right, so let's practice a couple more of these. looking at using these techniques, and then we'll turn our attention to some trig, one of the more important identities, and then we'll just sort of keep plugging along. All right, so let's start with this guy. Let's say we're going to take a limit as x goes to 4 of x squared minus 5x plus 4 over x squared minus x minus 12. So simple enough, some sort of a rational function here. So our first goal always is to try to plug in 4, because if it plugs in, everything works, then we're good. We don't have to worry about anything else. So try plugging it in. Let's see what happens. So we're going to get 4 squared minus 5 times 4 plus 4. On the bottom, we're going to get 4 squared minus 4 minus 12. And I'm sure it's going to come as no surprise that that thing is undefined. Gives us 0 over 0. Indeterminate form. We don't know what this is. It can literally be anything. So now we need to turn our attention to some other technique. All right, so the technique we want to use here is factoring. It's pretty obvious that factoring is going to be our best shot, mostly because the other things don't apply. There are no trig functions, so identities don't make sense. We don't have any square roots, so rationalizing doesn't do anything, which pretty much leaves factoring. But I imagine by this point in your math life, when you see things like this, you probably start thinking factoring anyway. So let's do that. Let's factor the top and bottom. So this function, if I factor the top, this is the good old quick AC method. 2 numbers will multiply to 4 and add to minus 5 are x minus 4 and x minus 1. And on the bottom, again, 2 numbers that multiply to minus 12 and add to minus 1 are plus 3 and minus 4. So this is what the factoring looks like. We see that there is a common factor of x minus 4, so we'll go ahead and slash those off. So what we know then is that this limit, the original limit that we started with, is actually the same as the limit as x goes to 4 of x minus 1 over x plus 3. So I'm going to harp on a point that I kind of made last time, and it's an important distinction. These two functions, these two things, the one we started with and the one we have after we reduced, are not the same. They are not the same functions. Their domains aren't the same, right? Like with this first one, 4 is not part of the domain. For the second one, 4 is part of the domain. So as soon as even something like that happens, they are not the same. But their limits are the same, because other than at the point x equals 4, these things are identical. Okay, so it's a minor distinction, but it's very important. And the only reason we can do what we're doing here is because we're not at 4. We're close. We're as close as you want to be to 4. Right? Imagine being as close as you can to 4 and still closer. Right? I mean, we can be just barely off of it, but we're not at 4. Anyway, so now, though, we get something that we can plug in, the 4, and what we see here is we get 4 minus 1 over 4 plus 3, which is 3/7. So this limit is actually equal to 3/7. Here's the deal. Remember those ways that we guessed? We drew the picture, right? And we just kind of followed along and we looked to see what the y value was. Or we plugged in x's that were nearby and looked for a pattern. This is one where you probably will not actually make a guess of 3/7. 3/7 is kind of a weird number. It's not got a good decimal. It's not one that you would actually recognize. 3/7 that's around like 0.43 something. And so you get some, numbers, and you might go, oh, it's getting close to 0.4 or 0.5, and you'd be off. And the same thing with looking at a picture. It'd be really hard to discern that it's 3/7. And that's why these techniques are super important, because if we can actually get the value, there's no guesswork anymore. And even if the value is weird, like in this case, 3/7, we got it. Okay, so factoring. It's a big technique for us. Let me show you another one with rationalizing. I know we did one last time, but rationalizing is one of those things that is a little bit less familiar than, say, factoring. So let's try another one. So let me change this limit. And let's try this guy. Let's look at the limit as x approaches 3 of, or not 3, how about 9? X approaches 9. The square root of x minus 3 divided by x squared minus 81. All right. So again, like always, let's plug it in and let's see what happens. So if we plug in 9, we're going to get the square root of 9 minus 3 over 9 squared minus 81, which again gives us the big old 0 over 0. All right, so we need to adjust this somehow. And what we're going to do is we're going to rationalize. So again, think about the different possibilities. There's trig identities, clearly no trig. Rationalizing, well, we do have a root, so that gives us a possibility. And factoring, and you might go, oh yeah, how about we do factoring, because the bottom can factor. You might see that's the difference of squares. That's great, but there's nothing to factor on top. So really, rationalizing is what we want to do. So with rationalizing, again, you multiply by the conjugate. And the conjugate, we're going to look at the piece that has the square root. And the conjugate is the same thing, but with the opposite sign. So in this case, there needs to be a plus instead of a minus. So I'm going to take both top and bottom, and I'm going to multiply by the square root of x plus 3. And as long as you multiply top and bottom by the same thing, we have no worries. Okay, so what this ends up giving us then, if you multiply the top out, right, if you FOIL that thing, it is a difference of squares. So you end up getting x minus 9. And on the bottom, I'm not going to multiply it out right now. I'm just going to leave it as x squared minus 81 times this conjugate. Now, if we plug in 9, we have the same problem that we had before, which is that we end up getting a 0 over 0. So what do we do now? Well, what do you guys think? What might we do this time? All right, so yeah, thanks, Bailey. So Bailey just put in the chat, how about factor the denominator? So remember when I was like, we can factor, but why bother? Well, we're going to bother because that is going to give us a factor that will cancel. So you take that x squared minus 81, that difference of squares. If we actually apply the difference of squares factoring to it, we get x minus 9 times x plus 9 times the square root of x plus 3. And now at this point, we can cross off those x minus 9s. So by doing that, we created a new function, but that function is identical to the one we started with, except for at x equals 9. And since we're just near 9, we're not actually at 9, we can actually evaluate this limit and get the same value. So we'll have the limit as x goes to 9 of 1 over x plus 9 times the square root of x plus 3. Okay, so this example really helps illustrate that sometimes we have to use more than one technique, right? We started with rationalizing, but then we also used factoring. So they're not independent. Sometimes they do go together. So you want to keep going until you can cancel out the piece that's causing the problem. And in this case, the bit that was causing the problem was x minus 9. All right, well, let's go ahead and plug this in then and get our value. So if I plug in 9, I'm going to get 1 over 18 times 6, because the square root of 9 is 3, right? And 3 plus 3 is 6. And this ends up being 1 over 108. And this is another one that if you actually tried to graph it, you would never make the guess of 1 over 108. And also, most likely, if you were to do this with like decimals, plugging stuff in with your calculator, you probably would not guess 1 over 108. More likely, you're going to guess 1.01, which would be the 1 over 100. So again, another situation where by actually going through the steps, we get the exact value, and we don't have to worry about making a guess that may or may not be correct. All right, so good for that, kind of seeing the process here with these guys. All right, so this is what we want to look for when we get 0 over 0. You want to try some of these kind of techniques. And I don't remember who it was last time. It may have been Erez who said something about, well, what if it's not 0 over 0? What if we end up with just a constant over 0? Let me show you how we deal with those with this example. So let's say we've got limit as x approaches, say, -2 of x squared plus 4 over x plus 2. All right, so again, like always, start by plugging in the -2. See what we get. So we get -2 squared plus 4 over -2 plus 2, which gives me 8 over 0. And again, this is undefined, right? Dividing by 0 is a problem, but it's not indeterminate form. It's not 0 over 0. Okay, so here's the distinction. This is undefined, but not indeterminate. Remember, indeterminate meant it could have any kind of a value. We just don't know what that value is. This cannot take on any kind of value. It's plain old just undefined. Okay, so the question is, what's going on here? All right, well, if you ever run into this situation, when you plug it in, if you get some number divided by 0, this means that you're going to get an infinite limit. Okay, so again, as long as it's not 0 over 0, it's some other number over 0, then we've got an infinite limit. And so really all we have to figure out then is it plus infinity or is it minus infinity? All right, well, there are a couple of different ways that you can do this. One is you can draw the graph. You can draw the graph and actually look at it. You're going to have a vertical asymptote at this point, right? So at x equals -2, there's a vertical asymptote, and you can literally just look at the graph and go, okay, am I going up? So that'd be positive infinity, or am I going down? What's going to be negative infinity? So that's what you could do if you wanted to do it graphically. You could also do it numerically. You could take a value near -2 and plug it in. Okay, so you plug in like -2.1 or something like that. and see what kind of number you get. It will either be positive or it'll be negative. And if it's positive, as long as you're close, if it's a positive number, you know you're going towards positive infinity. And if it's a negative number, you know you're going towards negative infinity. All right, now, what I do is a variation of that, a variation of plugging numbers in, but I don't actually plug in a number because I don't particularly care what value comes out. I only really care about what's the sign of that. Is it positive or is it negative? So here's what I do. When I've got a fraction, I look at the top and the bottom separately, and I just look to see, are they going to be positive or negative? Because since I'm dividing, if they're the same sign, the result will be positive. If they're different signs, the result is negative. All right, so let me kind of walk you through how I would do this. So we're approaching -2, so let's think about something just slightly smaller than -2. So let's start with the top. All right, so ignore the bottom. Just look at the top here, x squared plus 4. I'm going to make it so you can actually see it. There you go, so x squared plus 4. So plug in a number, a -2 point something, right? When I square that, it becomes positive, because a negative squared is positive. And then I add 4, that thing's going to be positive. In fact, I know that the top is always positive. Okay. I know that this is always positive just because when I square something, it's non-negative, and then I add 4, so that's always positive. So the top is actually always at least 4. So it's always positive. So now let's think about the bottom. Well, in the case of -2.1 or something that's just slightly smaller than -2, when I add 2 to it, it's going to be negative. Well, that tells me if I've got a positive divided by a negative, that I'm going down. So let me even start drawing the graph of this thing. I know that there's an asymptote at -2. Put that here. But what I already know is that as I'm approaching -2 from the left-hand side, so something just slightly smaller, it's going to end up going down towards negative infinity because I've got a positive divided by a negative. So now think about being on the other side. What if I'm at like -1.9 or -1.99 or whatever? Well, the top is still positive, but now the bottom, when I add 2, I'm going to get a positive number as well. So positive divided by positive is positive. So what I know about this thing is that at this asymptote, it's actually going down towards negative infinity on the left and up towards positive infinity on the right. And notice that I didn't do a single calculation. I have no idea what happens when I plug in -2.1. I don't know what the number is, but I still have an idea of what's going on with my limit. Now, if that didn't really track with you, because it doesn't always, and it's kind of a new way of thinking about it, that's okay. Use your calculator, plug in a number, you'll figure out whether it's going to plus or minus infinity. But a lot of these things that I share with you, I have up here for a couple of reasons. One, well, I'm a math guy, right? I've been doing this stuff forever. Like, I was about to say literally, that's a little bit hyperbolic. But I've been doing calculus. Like, I first learned calculus over 30 years ago. I mean, just think about that. I've been doing calculus for 30 years. So, obviously, yeah, I picked up tricks and all that. So a lot of this stuff you may not be really comfortable with and all that and be able to do right away because you're brand new to it. Okay, so just realize that. I've been doing calculus forever. But I also grew up in a time, I mean, if we're talking 30 years ago, I grew up in a time where we didn't have the technology that we do today. I didn't have something in my pocket that could just do all this stuff. So I had to learn ways of getting information without slugging it out, right? Imagine no calculator. I mean, we had calculators, right? But But just imagine you don't have a calculator and you need to plug in -2.1 to this and actually get a number. You can do it. It takes a long time, but you can eventually get a value. But if I don't care about that number, I only care if it's going plus or minus, notice that there are ways of getting there faster. So just always take these things with the proverbial grain of salt, because I am going to share a lot of these techniques. And there are going to be times you look at me and go, holy crap, how did he do that so fast in his head and visualize? Just keep these things in mind. A, I learned at a time where I had to use those tricks. And B, I've been doing this longer than most of you have been alive. That kind of frightens me, actually, as I say those words out loud. Anyway, so let's come back to this. We've got on one side, we're going down to minus infinity. On the other side, we're going to positive infinity. So what I'm going to write for this limit then is that this limit does not exist. I'm going to write dne or does not exist. There is no number that we approach. It just blows up to infinity. However, I do like keeping track of the fact that I am going to infinity. But the problem is with this one, on one side I'm going down, the other side I'm going up. So what do you think I'm going to do in order to get that information across but still be able to write like limits? How am I going to handle the fact that each side goes a different way?
You can use the superscript of positive and negative after the -2 to show it coming from left or the right.
Yeah, let's go to those one-sided limits, right? Remember that there is a way to show that. Those are the one-sided limits. So I'm actually going to break this into two different statements. The first one is going to be the limit as x approaches -2 from the right. So with the positive. This one then, I'll write infinity. So remember that little superscript, the exponent thing here. If it's a plus, that means we're coming from the right. And so from the right, when I was just a little bit bigger, I got positive values. So I'm going to write positive infinity. And then the other one-sided limit, so if we approach -2 from the left, then I'm going to write that as negative infinity. So this is a really good example where naturally we are concerned with one-sided limits since we're not going to the same place. All right, so if you ever have one of these where you've got some non-zero number divided by 0, it is going to be an infinite limit. And if you want to get to the which type of infinite limit, you do have to actually plug in values, draw the graph, somehow reason it out. Are you going to plus or minus infinity? And sometimes it requires breaking it into one-sided limits. Not always, because you can actually have functions that when you approach asymptotes, both directions go up or both directions go down. But this is not uncommon, as you guys are probably very aware. All right, so when you run into that, just we'll deal with it. All right, so let me give you another function here. And we're going to evaluate its limit. And this one, let's look at the limit as x approaches 0 of sine of x over x. All right, so we just introduced trig, which probably makes some of you a little bit nervous. Don't let it make you nervous. But let's look and see what happens with sine of x over x. All right, so we plug in 0. We always try that first, right? Just try plugging it in. So if I plug in 0, I get sine of 0 over 0. Please, 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 please fight the urge to cross off those zeros. We're at this beginning to cross off those x's because that's not how this works. This isn't sin times x. It's not sine times x. It's sine of x. So we have to make sure that we don't cancel things inside the sine with things outside the sine. Okay, but let's evaluate sine of 0. Sine of 0 is 0. So this leads us to the lovely indeterminate form 0 over 0. Okay, so that's great. Indeterminate form, which of course tells us nothing, right? We have no idea what this function is actually equal to. All right, well, so then we turn our attention to, or we move towards the, which of those different things are we going to try? So let's go down our list. Factoring. No, there's no factoring. There's nothing to do. What about rationalizing? Nope, no radicals. Then you go, well, what about identities? We got trig, got a sine. So you start thinking, okay, well, maybe there's an identity that will help us. Well, there's not really much you can do with just sine. If I gave you sine of x and said, hey, use identities to simplify or change its form, I don't know, there's nothing to do, right? When we've done identities before, it was always something more complicated. So we're kind of in a, well, what else is there on our list? And like I said, right now, we don't have anything else on our list, but let's start developing some things. So we're going to do a theorem right now. The theorem that's going to help us prove this one. And this theorem is called the Squeeze Theorem. And again, this is not a Bruce-ism. This isn't the way I say things. This is a technical name. You go to talk to anybody, and you tell them, oh, I learned about the Squeeze Theorem. If they've ever taken calculus, they know what you're talking about. As opposed to if you went and said to somebody, oh yeah, we were looking at a butterfly function, unless they came from my class, they're going to go, what the hell are you talking about? All right, so Squeeze Theorem. Here's how the Squeeze Theorem works. Is suppose that we've got 3 functions. And these 3 functions are such that they follow this inequality. Okay, so we've got 3 functions, f, g, and h. F is always less than or equal to g, and g is always less than or equal to h. So we have to be set up this way to use the squeeze theorem. So 3 functions, but they all go in order, boom, boom, boom. Okay, so we've got this. And suppose that the limit as x approaches c of f of x is actually the same as the limit as x approaches c of h of x. So I'm just going to call that limit L for the sake of having something so I can reference it later. But again, so we got these 3 functions with that inequality set up. But the 2 on the ends, the f and the h, they both approach the same limit. Okay, so this is everything you need in order to use the squeeze theorem. And if you have all of that, then it turns out that the limit as x goes to c of g of x is also L. So let me just talk for a moment about theorems and corollaries and all these other things that we prove, because for many of you, you may not have done much of this. There's always a necessary conditions part of the theorem, and that's this. Okay, so these are always things that must be true to use the theorem. They usually follow the if, or the word given. That's another one that you'll sometimes see. But these are things that we have to have. If we don't have these, then we can't use the theorem. Okay, so these are things that must be true to use the theorem. All right, and then we get a then, blah. And so this is just how logic works. If I make a statement, if statement 1, then statement 2, that just says that if you have all those initial conditions, then the next thing follows. All right, so if we've got this stuff, if we've got this setup, the squeeze theorem then tells us that this piece must also be true. And so I'm just going to put here that this is guaranteed. If the original conditions were met. So this is kind of how you have to read theorems, just in general. You look for what are the conditions, what do I have to have in order to use the theorem? And then if I've got those conditions, what am I guaranteed? All right, well anyway, so here's the squeeze theorem. Now, some of you might be able to look at that and go, oh, okay, yeah, I see it, I get it. More likely, the case is you're looking at it and you're going, this is like Egyptian hieroglyphics. I need a Rosetta Stone. Well, let me show you what's actually going on here. And I'm going to do it with a picture because I think a picture makes a little bit more sense. So I'm going to draw a graph. Let me start here with just some axes. And I'm going to put F and I'm going to put H on here. Okay, I'm going to put the two functions whose limit we know. So let's even specifically choose a place. So let's say that this is C. And let's go with an L value. So C is where we're approaching. L, that is the limit that I'm getting from the two that are on the ends of the inequality. All right, so let me draw them for you. So let's say that this is F. Okay, so this will be, nope, not F, this is H, sorry. So here's h of x. Here is a function whose limit as we approach C is L. Okay, so there's h. Let me give you an f. So maybe f is that guy. So this will be f of x. So has the exact same limit. At C, this function approaches L. All right, so cool with that so far? Those are the two functions such that their limits are the same. And we have that F is smaller than H. Always, right? At least less than or equal. It does turn out that they're equal at this one spot. But those inequalities say less than or equal. All right, well, now let's put in a G. And the only thing that we know about G is that it has to be bigger than F and less than H. So that means that however I draw it, it has to be between this red graph and this blue graph. Okay, so let me draw one that's between those. But notice that if I want to stay in between them, I'm getting forced into this point. So there's my G. So there's a function that is in between those other two. So again, notice that as we get closer and closer to C, this black one, G of x, it's getting squeezed by the other two. The other two are forcing it into the same place. So that's why we actually call this the squeeze theorem, because it's getting pushed in from above and below to the same point. So hopefully this picture helps you see why this is. Also why we name it, what we name it. But it is, this middle function is basically getting squeezed in to that spot. So in order to use the squeeze theorem, when you're given a function, and we're going to actually use the squeeze theorem on sine of x over x, what we need to do is find a function that's bigger and a function that's smaller that both go to the same place. Okay, so that's going to be our goal when we want to use the squeeze theorem. So before I actually show you how that's used for sine x over x, any questions on the theorem itself?
No, but Bruce.
Yeah.
When you're in focus mode, the camera is focusing on your other device that's catching your microphone. So the whiteboard's not coming up in focus mode.
You're not seeing the whiteboard?
No, not in focus mode. You can just pin the video of his phone, and that will just stay up on your screen instead.
So if you're on speaker view, what are you seeing?
Just your other profile picture for your.
Just my profile picture, but not this? All right.
Yeah.
Well, thanks. Thanks for letting me know that. I thought that this was concentrating on the whiteboard. That really sucks.
It is when you pin the video, but you have to go to where the frame of the whiteboard is, and you press the 3 dots, and then you press pin video, and then it'll keep it on that frame.
Right. The reason I'm saying that I'm concerned about this is I did this. I thought it was showing it on the speaker view, and the speaker view is what gets recorded when I put it up on YouTube. So people are not actually seeing the whiteboard then. Give me 1 second here, guys. I'm going to pause the recording. All right, so I just switched so that I'm getting caught by my device that actually has the whiteboard. So hopefully if someone's on speaker view, even if you have this unpinned, you're actually seeing the whiteboard now. Is that correct?
Yeah.
Yeah, okay. Well, then we'll just go with this guy right here. Okay, so thanks for letting me know. Was that you, Tim, who said that? Let me know that.
Yeah.
Okay, thanks. I appreciate it. Okay, so I'm going to hit record again, and then we'll pick this back up. All right, so maybe I didn't actually pause the recording. We'll see. Anyway, all right, so again, if you look at this picture and you kind of see what's going on, we've got H and F are squeezing G, forcing it into that position. Hence the name, the squeeze theorem, and why this actually works. So for those of you who are watching this on YouTube, I apologize if the recording isn't showing what I wanted to show. Technical glitch, but hopefully we're good now. All right, well, let's try this. Let me actually show you how we can use the squeeze theorem on a function like sine x over x. All right, so our goal is to find a function that's bigger than sine x over x and a function that's smaller than sine x over x that goes to the same place, goes to the same value. Okay, well, let's just first kind of see if we can get a feel for what's going on with sine x over x. So I'm going to bring us back to a lovely picture that you probably saw in trig. Let's go to a unit circle. All right, so here's our unit circle, and let's just remember how sine x was defined. So given an angle, my angle is my x. Actually, let's change this. Let's change the letter. Let's say that we're looking at sine theta over theta. I'm just going to change the variable name so that it's a little bit more familiar to us when it comes to the trig. So we got sine theta over theta. So let's put in a theta, and let's figure out what the sine is. So here is a theta. And then the sine of theta comes from this point right here. And the sine of theta is actually the y coordinate. So it's that right there. So that's how we actually define sine of theta given a unit circle, right? So we've got this right now. We know that the sine of theta is that little vertical piece, and there's our theta. So let's just think about what's going on. We've got sine theta over theta. Obviously, as the theta gets smaller, that angle gets smaller. This length also gets shorter. But it's a little bit hard maybe to see exactly what's going on in terms of that ratio. Now, I'm going to help you out just a little bit by reminding you about arc lengths. So if we want to measure the arc length here, that guy right there, anybody remember the formula for that? So the one starts S equals. Let's see, I'm not hearing anybody or anybody throwing anything up on the screen. It's given by S equals R times theta. And so since this is a unit circle, since the radius is equal to 1, we get S equals theta. And so another way of thinking about theta, other than this rotation, is you can actually think of it as the arc length of the bit of the circle that's mapped out as we rotate over to theta. Okay, so the reason I wanted to show it this way is what we're comparing when we do sine theta over theta is the length of this vertical red line, the ratio of that, and the curve on the arc. So now imagine that this angle starts getting smaller. How do you think those two distances are going to compare?
Wait, sorry, what is S in this case?
It's the arc length. It's the length of the curve. It's the green line. So let me exaggerate it a little bit on another circle here. So this would be the S. For our Y. So let me, so think about a circle that continues, right? Let me even throw in a different color here for my theta. So S is the length on the circle. Does that make more sense?
Yeah, thank you.
Okay. So theta is this green arc. Sine of theta is the vertical line. So like right now, which one's bigger? Which one's longer? The green curve or the red vertical line?
The green curve.
Yeah, the green curve, because it's not a line, right? There's a little, we're not just going down, we're also kind of going out. Okay, but if I make that theta smaller, in this picture, okay, which one's larger? The vertical line or the curve?
The curve still, but they're more similar.
Okay, so that's exactly right. The curve is still longer, but they're getting closer to each other, right? Those lengths are not as different because, again, think about as we're going on that curve, we're going down, we're also going out, but we're not going out nearly as much laterally as we were when theta was bigger. Okay, so it seems like as theta gets smaller, as those lengths get shorter, that those lengths actually get closer to each other. Well, that should give you an idea of what you think this limit should be. If I have two numbers that are virtually the same and I divide one by the other, what number am I going to get? What am I going to be really close to? What do you get if you divide a number by itself?
1.
1. So these two numbers are really close to each other. The number that comes out should be really close to 1. So just from this picture, it seems reasonable that this limit is maybe 1, that those two lengths are getting closer and closer and closer to each other. But I don't like the, well, it looks like it maybe possibly could be 1. So let's see if we can use the squeeze theorem. All right, let's see if we can use the squeeze theorem to help us out a little bit. All right, now to do this, I'm actually going to employ another trig function. So let me redraw this picture over on the side here. Let's get it a little bit less cluttered. All right, so again, here's our theta. We know our sine theta is this length right there. We know that theta is also the length of this arc. But I'm going to put another line out here. And this line is going to be a vertical line that comes from the x-intercept of the circle. So on the unit circle, that's out at the point 1, 0. Okay, so these are both vertical.
Bruce, sorry, but it's really hard to see in that one spot because of the glare.
Okay, thank you for letting me know. Let me try to adjust something real quick. Is that better? Not really. Now it's probably really dark. How's that?
That's good.
That's
Okay.
good.
All right, so basically that's a tangent line, right? It's the tangent line to that circle that goes up. But what I'd really like to know is what is its length? All right, well, check this out. You're gonna love this. So this one, its length is actually the tangent of theta. All right, so why is it the tangent of theta? Well, if you go back to how tangent is defined, right? Tangent is y over x on the unit circle. And y over x, this is actually the slope of the radial line coming out. right? Because think about slope as change in y over change in x. So that's actually the tangent of that line. And slope, again, is rise over run. And if you look at this one, the distance out here is 1. So that means our run is 1. So it turns out that the slope of that black line is such that the rise is actually equal to the slope. So that's why that rise is tangent. So if that just went, don't worry about it. I just verbally said that out for those of you who are like, why is that length tangent? It works out, just works out that way. It's also why these are called tangent lines, by the way, because that line is tangent to the curve and it ends up, its line segment is length tangent. Anyway, so we've got this now. So check out those lengths. So we had that red length, which was the sine of theta. We've got the green arc length, which was theta. And then we have that blue length, which is tangent. And so it should be pretty obvious from this picture that we've got now a relationship between these lengths, that sine of theta is less than theta. I'm going to put less than or equal to theta. And theta is less than or equal to tangent. So I'm just using a length argument. Red is shorter than green, which is shorter than blue.
Why are you calling the arc length theta?
Because it is length theta. That arc length formula, remember when you asked me about S? And we had S is equal to R theta.
Oh, because it's on a unit circle. That's right, okay.
This is 1, yep. So this is 1 times theta, or theta. All right, so here is an inequality that involves lengths. And this is maybe time for us to sort of step back again and go, what the hell are we doing here? Remember what our goal is. Our goal is to find a function that's bigger than sine theta over theta, and a function that's smaller than sine theta over theta, so that we can squeeze it into the one place. Well, I'm starting to create an inequality. This inequality has 3 pieces to it, which is kind of what I need. Now, I don't have sine theta over theta, but I can get there pretty easily. I'm actually going to start by dividing everything here by sine of theta. Right, with inequalities, we can do that. And when you multiply and divide, as long as you don't multiply or divide by a negative, you keep the same direction of your inequality. And sine of theta here is going to be positive. The way that I'm setting this up, it's going to be positive because I'm in the first quadrant. So no worries there. All right, so this becomes 1 is less than or equal to theta over sine theta. Can't really simplify that at all. But the tangent over sine, I can simplify. And that becomes 1 over cosine, because tangent is sine over cosine. And now if you look, I don't have sine theta over theta, but I've got its reciprocal, which is actually just as good. Because if I know where this goes, if I know where theta over sine theta goes, the reciprocal is just going to be the flip of it. right? So let's see if we can figure out this limit using the squeeze theorem. So basically, here's the question. Let's look at the functions that are bigger than and smaller than theta over sine theta. We've got 1 over cosine. So the question is, what happens to 1 over cosine as theta goes to 0? Well, if you plug it in, because remember, we always try first just plugging it in. We get 1 over the cosine of 0. The cosine of 0 is 1. So I know that this function, the bigger function, goes to 1. All right, what about the smaller function? What about the limit as theta goes to 0 of 1? The smaller guy. Well, what is that limit? It probably feels way harder than it is. Yeah, I think it was Bailey who just threw that in there. This limit is 1. Remember, if you have a constant, we had a limit rule that said constants, their limits are always that constant. So that guy's just 1. So notice what happened. We've got two functions whose limits are both 1. We've got a third function that's trapped in between those two. So it's going to get squeezed to 1. So by the squeeze theorem, what we know so let me just write this out here. By the squeeze theorem, then, we know that the limit as theta approaches 0 of theta over sine theta is equal to 1. Okay, that's what this work just showed us. The two outside functions both go to the same limit. Therefore, that inside function has to go to the same limit. All right, so by the squeeze theorem, we know that, which then just means by algebra, we know that the limit we're actually looking for, if we flip this thing over, also equals 1. Because it's just a reciprocal, right? You take 1 over 1, you still get 1. Had this limit been, say, a half, flipping it over would have given us 2. If this had been 2/3, flipping it over would have given us 3 halves, and so on. Well, 1, flipping it over, gives us 1. So this fairly simple looking function, sine x over x, required a bit of trickery to actually get its limit. But we've got it now. Again, I know this says theta and our original one said x. Doesn't matter, right? Change the names, that's fine. So this limit definitely does equal 1. So it seemed like it should be from the geometry, but now we've been able to prove it using the geometry. All right, so squeeze theorem is a bit challenging because you do have to get this inequality set up. And I know some of you might be looking at this specific one and going, oh my God, there's no way in a million years I would have figured this out. Yeah, I don't know that I would have either. I mean, maybe eventually if I played with it enough, right? But somebody saw it and we can, stand on the backs of giants. Okay, so Aaliyah said, why did I just flip it at the end? You mean when I went from theta over sine theta to sine theta over theta? Yeah, okay. The reason I flipped that is because the limit I was looking for originally was sine of x over x. And now now the light is giving us glare here, so it's kind of hard to see. Let me see if I can. Maybe hold on a second. Let me hold up that. I'll create a little screen here. Okay, so you look at that original was sine x over x equals 1, right? I wanted sine theta over theta, sine x over x. So that's why I flipped it over to get what I was looking at. And basically, the reason I could do that is since this other limit existed, and these are reciprocals, I know how to get the reciprocal of a number. I just flip it over. So I know you don't actually see it getting flipped over because 1 still looks like 1, but the reciprocal of 1 is 1. But that's why I ended up flipping it over, because I needed sine theta over theta. Does that make sense? All right. Okay, so it was kind of convoluted, difficult getting there, but this is one of those limits that you should know. All right, so let me stress that again. You should know this one. You shouldn't have to think about this. When you see it, you should just know, oh, I know what that limit value is. So let me put it in a box. That's how we know it's important, right? Let me put it here. So we're going to the limit as x goes to 0 of sine x over x equals 1. Know this. Okay, know this. In fact, it's so important, I'll put even some little red stars by it. I'll underline it. I'll throw in a couple more exclamation marks. Know this one, okay? Sine of x over x, it goes to 1 as x goes to 0. This is used all the time. In fact, I'm teaching second year calculus right now. We had to deal with sine x over x, I think on day 1, maybe day 2 last week. So it doesn't go away. For those of you who are going to go and take physics, you use this fact all the time. We call it the small angle approximation. But this is huge, okay? Don't worry about having to replicate the proof, but just know this fact, that as we go to 0, sine x over x goes to 1. All right, so now that we have that limit, we can actually do other limits that involve trig. And so here's another kind of big one. I mean, it's important. It's not as important as sine x over x, but it's still important. And this one looks like this. It's the limit as x goes to 0 of 1 minus cosine of x over x. Okay, so let's see if we can actually figure out what this limit is. So if we try plugging it in, like we always do, first step, we're going to get 1 minus cosine of 0 over 0. The over 0 should make you a little bit nervous because we already know it's not going to be defined. But let's see what we get on top. Well, cosine of 0 is 1. So we get 1 minus 1, which is 0 over 0. Okay, indeterminate form, which means we got to try something. All right, so you think about your different possibilities, factoring and conjugates, no roots, trig. All right, well, we're probably going to have to do something with trig. Now, this one, what we're going to do with the trig is what I call a miracle step. So if you've been in my classes, you know what a miracle step is. Miracle steps are those ones that someone says, well, just try this. And you go, well, why? Well, because it just works. The math gods came down and smiled upon somebody one day and went, hey, try this. Hey, it was a miracle. Okay, so this is a miracle step. What we're going to do is we're actually going to multiply top and bottom by 1 plus cosine. So again, if you were to ask me, well, why multiply by 1 plus cosine, I'm going to say, because it's what makes it work. But you'll see how it makes this work really quickly. Notice now, on top, if I multiply this out, I have a difference of squares. And so what that gives me is a 1 minus cosine squared. So when I FOIL it out, the OI part, the outside and the inside cancel each other out, and I'm left with 1 minus cosine squared. And on the bottom, I've got x times 1 plus cosine. But now we can use identities. And seeing a cosine squared probably just maybe made you perk up a little bit, thinking trig, because remember that biggie, the Pythagorean identity? Sine squared plus cosine squared equals 1. Well, if you use that, it turns out 1 minus cosine squared is equal to sine squared. So that was the Pythagorean identity. Let me just put here. By an identity. All right, so does anybody see why that was useful? Because at this point, it may just feel like we're doing things to do things.
You can use trig identities because isn't like sine over cosine like tangent?
Okay, that's a good guess. It's actually not what we're going to do. Let me just direct your attention to up here. The thing I just said, hey, know this. Remember that identity or that limit has sine of x over x? I got that now. I mean, there's other stuff in here, but I've got a sine over the x. So in fact, I can rewrite this. Let me just, so you can clearly see it. It's sine x over x times sine x over 1 plus cosine. And so what I can do, since I've got multiplication, remember what, from our discussion last time, that the rules of limits allow us to split these things up and calculate these limits separately. And so this first limit, we now know exactly what it's equal to, right? This, put it in a little blue box, that equals 1, because we just proved it. Sine of x over x is equal to 1. Which means if we can evaluate that second limit, all we have to do is multiply those two numbers together and we're good. Okay, so let's write out. This is going to be 1 times something. Let's see if we can figure out what that something is. Well, let's plug in 0 and see what we get. So we're going to get sine of 0 over 1 plus cosine of 0. Sine of 0 is 0. Cosine of 0 is 1. So that becomes 0 divided by 2. And 0 divided by 2, we can actually calculate. 0 divided by 2 is 0. So that first limit was 1. The second limit is 0. So we multiply those together, and we get 0. So this function, 1 minus cosine of x over x, as we get closer and closer to 0, that function gets closer and closer to 0. All right, so basically, this example is showing you how we can use previous knowledge. And a lot of what we try to do when we're presented with a function that we're not really sure about in terms of its limit, we try to do something to it so that it's like one we already know. And that's what we did here. We turned it into a bit that had sine x over x because we already knew what happened with that limit. So a lot of times with trig, it's a matter of massaging these things so that you get stuff you already know, like sine x over x. So let me show you one more with trig, another place where we can use identities to help us get it to look like one that we already know. But before I go there, any other questions on this one? Other than this miracle step? Okay, so let's try another one here. Let's go tangent. So let's look at the limit as x goes to 0 of tangent of x over x. Let me move it a little bit out of the glare. Okay, so this is the limit we're going to do. So let's plug in 0. Let's see what happens. So you plug in 0, you get tangent of 0 over 0. And the tangent of 0 is 0. So we've got an indeterminate form, which means, let's make our best guess. Let's see what we got. All right. So somehow I'd really like to be able to get back to an a limit that I know. And so when it comes to trig, we really only have 2 that we've done so far. But if you look at this form, you see you've got tangent of x over x. What should really be jumping to the forefront of your brain is, I'd really like to make this sine x over x. So how can we introduce a sine here? How can you get a sine from tangent? All right, so cool. The quotient identity, sine over cosine, perfect. So let's do that. Let's change this into sine over cosine. So we have the limit as x goes to infinity of sine x over cosine of x divided by x, which then from our algebra is the same as sine x over x times cosine of x. And then let's pull the exact same trick we just did, where we split this apart. So tangent of x over x, if you make use of the quotient identity, eventually we can write it as sine of x times 1 over cosine of x. All right, so now let's evaluate those limits individually. Okay, so we start with sine x over x. What happens to that as we go to 0?
approaches 1.
We get 1. All right, so that's 1. What about 1 over cosine? What's the cosine of 0? That's also 1. So we get 1 times 1, which is 1. So the limit as x goes to 0 of tangent of x over x is 1. Again, we made use of sine x over x. We just had to start with an identity to get us there. All right, so squeeze theorem is useful. It gave us sine x over x. We know what happens to that is we go to 0, which is useful because now we can employ that with other things. All right, so for a lot of these, it's just a matter of getting yourself to a spot where you can just plug it in or getting you to limits you already know. And so get ready for lots of algebra in trig to manipulate it so that we can actually evaluate the limits. All right, so that's the idea behind limits. Now that we've got those tools, we're going to use them when we develop calculus, because calculus is all about limits, by the way. At least when we set things up, we're going to use limits. All right, so the last topic I want to talk about is continuity. And I want to get us started. We're not going to get nearly as far as where we want to be because we only have 10 more minutes, but let's go ahead and keep moving here since we're still a little behind. So continuity. So when we talk about continuity, this is a property of functions. So functions are either continuous or not continuous. Okay, so it's kind of like all sorts of other properties. You either are or you aren't. Okay, so it's a property of functions. And so we have the two words here. We have continuous and non-continuous. So in the grand tradition of mathematicians naming things, well, if one of them is continuous, what do we call something that's not continuous? Not continuous. Okay, cool. All right, so non-continuous. So the question is, what's the difference? Well, let me give you the definition of what it means to be continuous. All right, we say that a function, f of x, is continuous at a point x equals c if 3 things happen. Okay, so there are 3 things that have to occur for a function to be continuous at a point. The first is that the function exists at that point. All right, so you can actually plug in the value and get a number out. So for a function, if it's not continuous, or sorry, if it's not defined at that point, it's not continuous at that point. So think about all the times that we ever say divided by 0. Those are places where the function's not continuous. Okay, so that's one of the things that has to happen. A second thing that has to happen is that the limit as you approach c of this function must exist. So not only does the function have to exist, but the limit has to exist. All right, so as we approach that point, the limit has to exist. So we've seen examples where functions are not, or where the limit doesn't exist. Those are also places where a function's not continuous. So we've seen that with like asymptotes, but we've also seen other functions where like the one-sided limits aren't the same. Remember that one that was absolute value of x over x? it was like a horizontal line here, another horizontal line that was lower. And so basically what we ended up seeing was something that looked like this. That's not continuous because the limit doesn't exist. Okay, so that's the second thing that has to happen. So function exists, limit exists. And then the third thing that needs to occur is that these two values, whatever that limit is, actually has to equal the function value. So it's not just enough that the function and the limit both exist, but they have to be equal to each other. All right, now in some books, and I'm not actually sure what our book shows, some books will show only this third condition. Because when you write this statement, it sort of implies that the limit exists and that the function exists. I like to write it out separately because it's important to realize that it's necessary for the function to exist. It's necessary for the limit to exist. And this helps you see different types of problem spots. Okay, because not all problem spots are the same when it comes to continuity. We need to be able to recognize which one they are. So that's why I like to list them out as three separate things. Okay, so this is what it means to be continuous at a point. Okay, so this is just continuous at a point. But if we're going to talk about like a function altogether, what does that mean for continuity? So the next thing I want to give you is what it means to be continuous on an interval. Okay, so we say that f of x is continuous on an open interval a, b. So just think A and B are numbers. Open interval just means that we're not including the endpoints. Okay, so that's why I use parentheses here. But we say that it's continuous on this interval if it is continuous at all points in the interval. So that should kind of make sense, right? If we're going to want to be continuous on an interval, it just means that we're continuous at all of the points in that interval. All right, so these are the three things that we need to have continuity. So let me give you some more terminology, because these are some words you're going to hear. So I put here continuous and then non-continuous. There is another way of saying non-continuous. You'll sometimes see discontinuous. So you can be continuous or discontinuous. And the reason I brought up that word is for this next term. Any place where a function is not continuous, we call a discontinuity. All right, so points where a function is not continuous they're called discontinuities. And we're going to see these. We are definitely going to find discontinuities because there are places where functions don't exist, where limits don't exist, where the limits don't equal the function value. So those are called discontinuities. So really what our goal is going to be is, given a function, we're going to try to find the discontinuities. So we're going to try to find those problem spots. Because then, the other interval, I'm sorry?
Oh, sorry. I just had a question about the three rules. Does that mean that it has to actually hit that the function has to actually hit C, or can it still just be approaching C?
Okay, so for the limit, we're only concerned about getting close to C. But for the first one, f of C, that one we do have to be at C. Right? That very first line about the function must exist, f of C must exist, that means we can plug in C.
Okay, so those three rules put together means that it actually will touch C.
Yes.
Okay,
Yeah.
thank you.
We'll talk about what this means in terms of the graphs next time. And basically, we're going to be able to determine discontinuities visually by looking for those kinds of problems. Like, what does it mean if the function doesn't exist? What does it mean if the limit doesn't exist? What does it mean if they're not equal to each other? And so then we can even start classifying discontinuities, because we classify them by types, because they're not all created the same. Some of them you can kind of ignore, others you can't. So we'll definitely talk more about that next time in terms of what it means graphically. And but for it to be continuous, for all three of those things to occur, we definitely have to be able to go through C, for sure.
Thank you.
Oh yeah, you're welcome. Okay, I think this is probably a good place to stop. So let me just remind you real quick that we do have our first quiz on Friday. And the quiz on Friday, remember, it is going to be at the start of class. It will, if you go onto the assignment list, you'll see that it's already there, but it says that it's unavailable. It won't be available until 8:30 on Friday morning. It's just a PDF. So you can, just pop it up on your screen, print it out if you want, whatever. But what you're going to do is you're going to work out those problems either on your printout of my quiz or on a separate piece of paper. Then you're going to upload a PDF scan of it. If you do not have a way to PDF scan, it's really easy. If you've got a phone, a smartphone, you can get an app. There are tons of apps out there that will scan things as PDF. But I really kind of need it to be a PDF for my grading program. For this first one, if you still don't really have access to that or you're having difficulty, a picture is fine as well. You can take a picture and upload it, but I definitely prefer a PDF. For the first quiz or two, I'll let you do PDF, other files other than PDFs, but when it comes exam time, I'm going to require it must be a PDF. So if you don't have a way of doing that yet, contact me. Let's work on it, get you access to what you need. But anyway, it's going to turn on at 8:30. You need to have it uploaded by 9:10. Okay, so and this one, there is a cutoff. Like, the computer will cut it off. You try to upload it after, and it will not let you. Okay, do not push it. The intention of this quiz should not take you more than 20 minutes. The other 20 minutes are basically to deal with technological issues. Okay. So in terms of an app that I recommend, I don't know that I have one that I recommend, but I do know an app that I do use. It's called Cam Scanner. That's the one I use personally. But I know that like my son's got one through Google, right? So if you've got a Gmail account, I think sometimes there are even built-in ones with that. So, but the one I use is called Cam Scanner. Anyway, so that quiz is going to be on Friday. As soon as the quiz wraps up, I'm going to start class at 9:10. So I'll be back in on Zoom and we'll do 9:10 and go from there. In the future, is it okay if we take a picture with Cam Scanner and then turn it into a PDF from there? So Lee, I don't know if I quite understand that question, because with Cam Scanner, you take a picture with your phone and it converts it into a PDF immediately. So then you just will have that file and you can upload it.
Okay, yeah, I was just checking that you were just saying in the future you didn't want us to take a picture, but do you just mean if it's not in PDF form?
Yeah, what I'm saying is that in the future I'm going to require PDFs, but like right now you can send me a JPEG, right? You can send me other kinds of files, that's fine. But for me, just the ease of grading things, it's better if everything's a PDF. Okay, so in terms of what the quiz is going to cover, it's going to cover things through 2.1. So basically the stuff that you did homework on for the first set. So a little bit of pre-calculus review, and then the preview of calculus, right? Those problems where you had to find slopes of secant lines, find areas, stuff like that. So it shouldn't be a big deal, I promise. It's just going to be like 3 or 4 questions. Mostly I just want to make sure you guys are keeping up with things, okay? But just realize that that's going to happen Friday, okay? I will post a message in Canvas reminding everybody, kind of sharing the same information, but just be aware that that's what's going to happen on Friday. So we'll start with the quiz, then we'll continue our discussion of continuity. All right, so any other questions before we call this a day? All right, well, then with that, you guys have an awesome couple of days. Again, I apologize for technical issues. Thank you for letting me know about that, though, Tim. I appreciate it. Other than that, I will see everybody on Friday. All right, adios.
Thank you, Bruce. See you on Friday.